All right, guys, the last thing I want to talk about in this section is Newton's law of cooling. Okay. So let me tell you the situation for this. I'll use a personal example. If you've ever eaten one of those frozen pizzas, you know, the ones you have in the freezer and then you can put them in the microwave. Okay, usually it takes, 2.5, 3 minutes. Or anything maybe you put in the microwave. When you pull it out, a lot of times it's really hot. You don't want to eat it right away, right? And I would be surprised if there wasn't someone else who might do what I do. Is a lot of times I'll take it out and I'll put it in the freezer. And my reasoning is, well, it's going to cool down faster in there and then I can eat it sooner if I'm really hungry. Okay. That is an example of Newton's law of cooling. What it says is if you put something that's hot in a cooler temperature than what it is, it's going to eventually cool down to that temperature as time goes to infinity. Okay, and that seems to make sense. If we left the pizza in the freezer for a really long time, then it's going to get close to the temperature of the freezer. Of course, we'll probably take it out in a few minutes, right? This is also, if you think of things, some of the TV shows, the detective shows, where they try to figure out when someone was murdered, this is something they actually use to see, well, the temperature of a normal human body is 98.6. Well, if you found a dead body and the temperature is at 90 degrees, you can use Newton's law of cooling to figure out, okay, well, I think they were killed around this type of time. So there's one practical sort of application. So in this formula, we call T sub 0 the ambient temperature. That is the same as the surrounding temperature. So for our pizza example, this is like the temperature of the freezer, okay? The surrounding temp. T is the amount of time. Once again, the units depend on the context of the problem. And C and K are constants to be found. So there's going to be an extra constant to find in this. So what I want to look at is I want to look at number 28 in the book. Okay? And what number 28 tells us is that a piece of metal is heated to 300 degrees Celsius. So we're talking really hot, probably red hot. And then it's placed into a liquid at 50 degrees Celsius, which is still pretty hot. That's, I think, about 130 degrees Fahrenheit, but it's much cooler than the 300 degrees Celsius. After 4 minutes, the metal is cooled to 175 degrees Celsius. That makes sense since the ambient temperature is much cooler. Find its temperature to the nearest hundredth after 12 minutes. Okay. Now it says hint, change minutes to hours. I think it's probably easier to leave it in minutes personally. Okay. But you can do that if you'd like. So let's go through. Let's figure out how hot this metal will be after 12 minutes. So let's write down what we know. We know, so we have our model here, that T sub 0, the surrounding temperature, is 50 degrees Celsius. We also know a few other things. I know that F of 4 at 4 minutes, that the temperature of the metal is 175 degrees Celsius. I also know, even though this may seem redundant, that F of 0 is 300 degrees Celsius. Finally, what I want to know is F of 12. What is that equal to? What is the function value? Okay, so let's start with our model. Okay, that's our F of t equals T sub 0 plus CE to the negative KT. So to be able to figure this out, I got to plug everything in. I got to determine K and then plug in 12 for T, okay, because this is a function of time. So first of all, I know what T sub 0 is. F of t is equal to 50 plus CE to the negative KT. Nothing too hard so far. Now, I'm going to go ahead and use this little bit of information right here. Let's call it A. If I use A, F of 0 equals 300, I know 300, the function value, is equal to this when T is 0. CE to the 0, oh, I guess 300 equals 50 plus C. I think I just determined C. C is equal to 250. So see how I used A to determine what C is. So now my model is F of t equals 50 plus 250 e to the negative KT. The only constant I don't know is K, but I have this information. Let's call it B. And you can tell what I'm going to use now. So when the function value is 175, that happens when t is equal to 4. So I have 50 plus 250 e to the negative 4k. So I'm right here. And let's see if we can solve for K. Let's get rid of that pesky 50. 125 equals 250 e to the negative 4K. Now what would I do? Well, if I want to take natural logs of both sides, I mean, to tell you the truth, we can honestly right now, but it just makes the math a little harder. Why don't we divide out that 250 from both sides? So that 1/2 is equal to e to the negative 4K. Now we're ready, we're in business to take natural logs. Natural log of 1/2 equals natural log e to the negative 4K. Swing that negative 4K out front. Natural log of 1/2 equals negative 4K times natural log e, which we know is 1, so that's fine. And it looks like K is equal to negative 1/4 natural log 1/2. Well, that's great. I have K, okay? If I round that off, that is about 0.1733. Okay. So let's take everything together now. My model is f of t is equal to 50 plus 250e to the negative 0.1733 t. That's my K value, rounded to the nearest 10,000. And we want to know after 12 minutes, what's the temperature of this metal? That means we need to know what F of 12 is. Well, that's 50 plus 250 e to the negative 0.1733 times 12. Okay. If you punch that in, what you should be getting is about 81.25 degrees Celsius. This is used in a lot of engineering applications to try to see what the temperature possibly of some metal, some rod, something like that can be. And we can even reverse the question. We can say, well, when would it be down to, say, 70 degrees Celsius? So just like with the other ones. That wraps up 4.6.